the radioactive particle bounces off it. And it has to be positive, so we've got this repulsion. So alpha particle comes in, it hits the nucleus, it repels, and it bounces back. So Rutherford realized that, yes, electrons exist, but yes, most of the atom needs to be empty space, and yes, there needs to be a small solid bit of positiveness in the middle. And so the middle bit he called a nucleus, then there was nothing, and then around the outside there was electrons. And this became known as the solar system model. So people were getting into space and discovering planets then. So like the solar system, the nucleus was in the middle, then there was nothingness, and then there were electrons in orbits. So yeah, astronomy was very much in vogue by that time. Uranus had been discovered by Herschel, and then maths had been used to predict that Neptune needs to be found, and it was found. And then in the 1930s somebody found Pluto. So the solar system model, and again the solar system model is the model of the atom which a lot of people who haven't really done much beyond high school science still think of when you say an atom. So if most of an atom is empty space, why the hell don't you see through stuff? And the answer to that really was these electrons, they're kind of like a swarm of orbiting electrons. They buzz around so fast, and in like sort of 3 dimensions. This is like a very sort of 2-dimensional drawing, but you know, if you think of orbits going round and round and round and like that, like you see pictures of, then it's like a swarm of orbiting electrons, and I suppose it's like a fly's wing. You know, they beat so fast in all sorts of directions that you don't really see through stuff. So it's a swarm of orbiting electrons, and this was the Rutherford solar system model. But there was a problem with the Rutherford solar system model. If you think of an Earth orbiting satellite, I don't know if you've seen these programs, the documentaries, there have been a few about how you build an Earth orbiting satellite. They're actually quite interesting. One of the things you'll see is that satellites need and are given little thrusters. They have little thruster engines, little rocket engines, and a supply of fuel. Now, why do they need to do that? Well, because in orbit, because of the pull from gravity, over time a satellite is very gradually pulled down. Its orbit very gradually gets lower, and if nothing is done, then over time the orbit gets lower and lower and lower until it actually gets down to the Earth's upper atmosphere, and then it burns up. So satellites need little thrusters and a fuel supply to keep boosting them up when they go down a little bit. So that's why on these programs where you see satellites being constructed, they also have a little rocket engine and a supply of fuel which kind of boosts them back up. Now after about 10 years or so, then this fuel supply runs out, and so they do descend and they do burn up. This is actually okay for spy satellites, because after about 10 years then camera technology has usually advanced so much that, you know, the military is wanting to put a new satellite up there with this new generation of camera on. So really the fact that this is going to burn up after about 10 years is actually quite convenient. It gets rid of space junk, and they would have wanted to put another satellite up anyway, so it's not so much of an issue. Anyway, gravity is quite a weak force. It's one of the, well, it's the weakest of the fundamental forces. It doesn't seem weak to us, but you know, if you imagine picking up a bag of shopping, that's got the whole planet pulling it down, and yet without too much issue you can lift up a bag of Tesco shopping. One person can overcome the pull from an entire planet. Now electrical forces are very much stronger. So if you did have electrons orbiting like the satellite orbits, then in probably nanoseconds the electrons will be pulled in to the nucleus, and presumably the atom would implode and everything should implode, and we wouldn't be here talking about it. So the solar system model was found to be wrong, even though it was better than the Jimmy Thompson model of spotted dick or plum pudding. Then World War I happened, and the world imploded. After World War I, something called quantum physics came about, and quantum physics came about because of those light curves we talked about a while ago. But quantum physics, the big place where quantum physics was happening was in Copenhagen in Denmark, and sort of the big hitter, he wasn't the first, but a very big hitter was a guy called Niels Bohr. And the Physics Institute was built by Carlsberg. So there's my lovely drawing of a pint. So it was the Carlsberg Physics Institute in Copenhagen, where this quantum physics, so the physics of the very small, was discovered, invented, whatever. Anyway, Niels Bohr said atoms are not like solar systems. Atoms are like a block of flats. So this Institute of Physics, yes, they did a lot of physics, this Carlsberg-sponsored Institute of Physics. They did a lot of physics, but they also drank lots of beer, and they did crazy stuff like clambering down from high-up windows down to low-down windows, then if they're feeling energetic, clambering up from low-down windows to upper windows. And that sort of inspired Niels Bohr to say, well, an atom is actually like a block of flats. And like a block of flats, there are certain floors, and the electrons exist on certain of these floors. And the nucleus of an atom is like the ground floor. So an atom is like a block of flats, electrons exist at certain levels, and the nucleus is at the ground floor. This doesn't really have to make sense. One of the key ideas about quantum physics in Copenhagen, in fact it was called the Copenhagen interpretation of quantum physics, was if you have a model which seems to work, it doesn't matter if that model doesn't make a huge amount of practical sense in real life. If it works, go with it. Albert Einstein hated it because it didn't really make sense, but this is how quantum physics is. It doesn't make a lot of sense in terms of what's really going on, physical processes, but it definitely seems to work. So the Copenhagen interpretation is get your ego out of the way. You don't really need a pretty mental model, a pretty mental image. If we've got something which works, just turn the handle and make it work. Anyway, so here's an atom, and the idea is if you make an atom hot, so for example we talked about a block of iron before, so let's stick some iron in a fire. Can you see all these electrons are now jumping up to higher energy levels? Now, yes, most of the electrons will be jumping up, but then also when they get towards the top they will fall down, and then because they're still being heated they go up again, they fall down again, go up again, fall down again. But when they fall down, when these electrons jump down, they lose energy because you're going from a high up floor down to a low down floor. They lose energy. You could think of it as they're losing gravitational potential energy, as a vague analogy, but they lose energy and they give out a photon of light, and this is why hot things glow. So here is an electron jumping down from a higher energy level to a lower energy level, and it's giving out a photon of light. Now the energy of a photon is given by the formula E equals hf. So if you have a figure for what the energy level here is, so you've got a number for that energy level and you've got a number for that energy level, you've got the energy at that level and the energy at that level in joules. If you do E2 minus E1, E2 is the higher of the two energy levels, E1 is the lower of the two energy levels. It doesn't have to be the second and the first. This could be the fifth level and that could be the third level, for example. So the difference in energy levels equals hf, where h is Planck's constant and f is the frequency of the photon given out. So E equals hf. E, the energy of the photon, h is Planck's constant, look it up on the datasheet, and f is the frequency of this photon given out. So if you have numbers for the energy of these energy levels, then you can work out the frequency of the photon which is ejected when electrons do that particular jump down. So yes, this drunken jumping picture of atoms, inspired by the members of the Carlsberg Institute climbing down and leaping down between windows in their institute, it doesn't really sound reasonable, but that's quantum physics for you. So how can we see these energy levels? Can we see these energy levels? We can virtually see these energy levels. It's a slight indirect picture, but we can virtually see the energy levels themselves. If we've got something which is hot, a hot element, let's say you're sticking some, I don't know, sodium in a Bunsen burner flame, you're making it really hot. Well, these electrons are jumping down, constantly jumping down energy levels, so this burning lump of sodium is giving out photons of light. Okay, maybe it's hot iron. And then if you have a prism in a tube, then this prism in a tube will separate out these different color photons. They're different colors because they come from different jump downs, and it separates them out into these colored bands. It's a line spectrum. And how bright these colored bands are depends on how many electrons are doing the jump, and the position of these color bands shows you the size of the jump down. So if this is the very sort of high wavelength end, then high wavelengths come from small jump downs because E equals HF, so small jump down gives you a small frequency, so small frequency is a long wavelength, so this might be the long wavelength end, this might be the short wavelength end. Short wavelength means high frequency, which means a big jump down between the energy levels. So yes, this shows you small jump downs, big jump downs. Small jump downs mean low energy photons, low frequency, long wavelengths. Big jump downs show high energy, high frequency, short wavelength light. And how else can this otherwise be explained? Yes, quantum physics ideas are weird, but they perfectly describe nature. This bunch of stuff with energy levels, you can see this with the colored lines from a spectroscope. And if you're saying this doesn't make sense, we want another mental model, we actually want to see the solar system model or whatever, then you need to come up with a different way of explaining this. Whereas blocks of flats seems to beautifully explain this. So that's our current understanding of what stuff is made of, or what electrons are made. Sorry, what atoms are made of. Now, it's also the case that if photons of light come into an atom, if the energy of the photon matches the energy difference between two floors in the block of flats, then that electron in the lower floor can absorb the energy from that photon and jump up to a higher energy level. That incoming photon has to have the exact amount of energy which is in between the two floors in question, otherwise it won't be absorbed. But if it is absorbed, the electron will jump up. And both jumping down and jumping up, you use the same formula, E2 minus E1 equals HF, where E2 is the higher of the two and E1 is the lower of the two. Now it's worth saying that the energy levels are negative. The energy at the top of the block of flats is 0, so the energy levels below are negative. But just go with the negative numbers, put them in brackets, treat negative numbers as you normally do in maths, and the right answer will come out. So if you fire photons in, and the result of that is that electrons can jump up energy levels, the next logical question is, well, if you have a photon which comes in with enough energy, can you jump the electron completely out? And yes, you can. The minimum energy photon, the minimum energy that a photon, incoming photon, needs to have to jump the electron out, completely out of the block of flats, is called the work function energy, E, the work function energy. Now again, E equals HF, we always use this formula when dealing with photons, but a photon with energy to jump the electron out of the block of flats, it has work function energy, and the frequency of this photon, if it has sufficient energy, if it therefore has, because the frequency decides energy, so if it has sufficient frequency for the energy to be the work function energy, then that's minimum frequency we call is the threshold frequency for the metal. So the threshold frequency is the same idea as the work function energy. It's the frequency that an incoming photon needs to have to jump the electron out of the block of flats. Now this is exaggerated a little bit. Actually, the work function energy, the threshold frequency, is the energy needed just to sort of dribble it over the top and not have any more energy. It's not to fire it out with the speed of 1,000 gazelles, as I seem to have implied there. It's just the minimum energy needed to get the electron out of the block of flats, but just to sort of dribble over the top and not too much more. So why do we care about this? Well, this is how all digital devices which detect light and work with light do it. So, for example, digital cameras, motion sensors, automatic doors, night vision, thermal imaging, digital televisions. Photons of light come in, and electrons are jumped out of the block of flats.